Dear students, welcome all of you. So in previous class, we discussed about the properties of congruence, Fermat numbers, and yesterday we see that the cancellation of non-zero common factors from both members of congruence is not possible. That is established by using an example. That it means 48, which is congruence to 18 mod 10. So we cannot cancel the common factor. Here 6 is the common factor of both sides of this congruence. So if we cancel it, we get 8 congruence to 3 mod 10, which is not possible, which is a wrong idea. So it is non-congruence to 3 mod 10, means the cancellation of non-zero terms from both sides of the congruence is not possible. Now, so what is the condition which applied for this cancellation? Is the cancellation possible if it is subjected to certain condition? That's our next answer. So, consider this cancellation loop. Means if AC congruence to BC mod M, AC congruence to BC mod M, and let D is the GCD of M and C. Here M means the modulus and C be the common, which is common on both sides of this, on both members of the congruence or the common factor. Then if D be the GCD of this modulus and common factor, then we have A congruence to B mod M by D. So this is the condition for the cancellation law with respect to the congruence. If AC congruence to B mod M and D be the GCD of this M and C, means the modulus and the common factor, then A congruence to B mod M by D. How? That means a common factor C can be cancelled provided the modulus is divided by D is D means the GCD of M and C. So how? Here AC congruence to BC mod M. AC congruence to BC mod M means M divides is given, M divides AC minus BC. M divides BC minus AC minus BC. So that means M divides C into A minus B. So clearly that means M by D divides C by D into A minus B. But what is D? It is given. D is GCD of M and C. So that means M by D and C by D are relatively primes to each other. Here M by D and C by D are relatively primes to each other, as well as M by D divides C by D into A minus B. Clearly M by D and C by D are relatively primes to each other. We know that M by D does not divide C by D. Thus this gives M by D must divide A minus B. M by D must divide A minus B means A minus B is congruence to 0 mod M by D. That means A congruence to B mod M by D. Okay. So the cancellation is possible when common factor C can be cancelled provided the modulus is divided by the GCD of that modulus and common factor. So here, now when D is 1, means M and C are relatively prime. When the common factor and modulus are relatively prime, then AC congruence to BC mod M should imply A congruence to B mod M. Okay, that is the special case here. Means if D is 1, if D is 1 means the modulus and the common factors are relatively prime, then AC congruence to BC mod M should implies, that implies A congruence to B mod M. B mod M by D, here D is 1. So when the modulus and common factors are relatively prime, then the cancellation is possible immediately. That is AC congruence to BC mod M should implies A congruence to B mod M. So the cancellation of common factor is possible when it is divided by the GCD of modulus and the common factor. So this is the cancellation law regarding the convergence. Agree? Now, by using these arguments, we consider certain theorems. Consider assume A congruence to B mod A. There is a theorem. Assume A congruence to B mod A. Assume A congruence to B mod A. If D divides M, if D divides M and D divides A, and D divides A, then D divides B. If D divides M, D divides A, then D divides B. How? Here the proof is so immediate. Why? A congruence to B mod M means M divides A minus B. Okay, M divides A minus B. If D divides M, D divides M, M divides A minus B, this implies D divides A minus B. M divides A minus B, and if D divides M, then D divides A minus B. D divides A minus B means what do you get? A minus B congruence to 0 mod D, that is A congruence to B mod D. Here A congruence to B mod D. If D divides A, that is given, if D divides A, that means D divides A minus 0, that means A congruence to 0 mod D. So consider this is A congruence to B mod D, and consider A congruence to 0 mod D. So what is 2 minus 1 or 1 minus 2? 1 minus 2 gives vertical subtraction, that is 0 congruence to B mod D. 0 congruence to B mod D. 0 congruence to B mod D means D must divide B. So if A congruence to B mod M and D divides M and D divides A, then D should divide B itself. Agree? Come to the next result. If A congruence to B mod M, if A congruence to B mod M, then GCD of A and M is same as GCD of B and M. If A congruence to B mod M, then GCD of A and M and GCD of B and M are same. That is, the numbers which are congruent to mod M, the numbers which are congruent to B mod M should imply B congruent to A mod M. So the numbers which are congruent to mod M have same greatest common divisor, the same greatest common divisor with M. The numbers which are congruent with the mod M has same GCD with M. How to prove this one? So for to prove GCD of A and M equals GCD of B and M, that is the requirement. So that D is GCD of A and M. The G is GCD of A and M, and E equals GCD of B and M. Agree? D is GCD of A and M means D divides A and D divides M. Okay. E equals GCD of B and M means E divides B and E divides M. But A congruence to B mod M. A congruence to B mod M means we have it is given M divides A minus B. M divides A minus B. A congruence to B mod M means M divides A minus B. But what is D? M divides A minus B, D divides A, and D divides M, that implies D divides A minus B. Okay. D divides A minus B, but D divides A. Here consider D divides A and D divides A minus B. So that should imply D divides A minus of A minus B, that means D divides B. Agree? Again consider means D divides M and D divides B. D divides M and D divides B. D divides M and D divides B. That means D divides E. Why? Because E is the GCD of B and M. Enough. So D divides E. Again, Again, here E divides M divides A minus B. So E divides M and M divides A minus B. That should imply E divides A minus B. E divides A minus B. Okay, E divides A minus B. But E divides B also. E divides A minus B and E divides B. So from here you have E divides A minus B plus B, that is E divides A. E divides A minus B plus B implies E divides A. So here E divides A and E divides M. E divides A and E divides M. That means E divides D. Why? Because GCD of A and M is D. So E divides D and D divides E. Combinedly you will have E equals D, means they have GCD of AM and GCD of A and M and GCD of B and M are same. Okay, right. Now consider another result. If A complements to B mod M and if A complements to B mod M and if 0 less than or equals modulus of B minus A strictly less than M, 0 less than or equals modulus of B minus A strictly less than M, then A equals B. Then A equals B. If A complements to B mod M and if 0 less than or equals modulus of B minus A strictly less than M, then A equals B, provided A minus B differs from 0, or simply then A equals B. That is what we prove. So how? So this can be proved by using the following arguments. A complements to B mod M means it is given M divides A minus B. Okay, M divides A minus B. M divides A minus B means surely this M less than or equals modulus of A minus B, provided A minus B differs from 0. Okay, M divides A minus B means M less than or equals modulus of A minus B. But it is given, given modulus of B minus A strictly less than M. This happens only when A minus B equals 0. Therefore, A minus B equals 0. A minus B equals 0 means A equals B. So that proof is immediate. Enough. Now, consider another result. Suppose A is complements to B mod M. If A complements to B mod M, if and only if A complements to B mod M, if and only if A and B give the same remainder when divided by M. A and B give the same remainder. A and B give the same remainder when it is divided by M. So the theorem is important. Then come to its proof. A complements to B mod M. A complements to B mod M means we have M divides A minus B. But to prove, we have to show that this A and B give the same remainder when it is divided by B. Now suppose letter A equals MQ plus R by division algorithm. It is 0 less than or equals A equals MQ plus R, 0 less than or equals R strictly less than M. And B equals some MQ plus R, where 0 less than or equals capital R strictly less than M. Okay. So come to the choice of R and R. Means here it is modulus of R minus R strictly less than M. Okay, modulus of R minus R strictly less than M. So A equals MQ plus R and B equals MQ plus R. What about A minus B? Here A minus B. A minus B equals M into Q minus Q plus R minus R. M into Q minus Q plus R minus R. That means a minus b equals m into q minus q plus r minus r means this m must divides, yes, a minus m must divides a minus b minus of r minus r. Okay. A minus b equals m into q minus q plus r minus r. So means this m divides a minus b minus r minus r. A minus b. Now c congruence to some d, c equals or d equals some c plus n. So here m divides a minus b minus r minus r. A minus b minus r minus r means what is a minus b? A minus b congruence to r minus r mod m. Okay. A minus b congruence to r minus r mod m. We have mod 0 less than or equals r less than m and 0 less than or equals capital R less than m. So combinedly we have 0 less than or equals modulus of r minus r strictly less than m. Agree. Then we have, but what is a congruence to? It is given a congruence to b mod m. That means m divides a minus b. Clear? M divides a minus b. Also we have m divides a minus b. Also we have m divides a minus b minus of r minus r. Enough? So from here m divides a minus b, but m divides a minus b minus of r minus r. Surely m divides r minus r. M divides r minus r. M divides r minus r means m less than or equals modulus of r minus r. M less than or equals modulus of r minus r. M but 0 less than or equals mod r minus r less than m. So that should implies r equals r minus r equals 0. That means r equals r means they have same remainders. That is, if a congruence to b mod m, then b and a give the same remainder which is divided by m. So the first part is immediate. So the first part is finished. Now the reverse integration is so immediate. Why? If a and b give the same remainder, a and b give the same remainder means suppose a equals some mq plus r and b equals some mq plus small r means a and b gives the same remainder when it is divided by m. A equals mq plus r and b equals mq plus r. So what about a minus b? A minus b equals m into q minus q. Agreed? A minus b equals m into q minus q means m must divides a minus b. M divides a minus b means a congruence to b mod m. So the reverse integration is immediate. So if a congruence to b mod m or a congruence to b mod m, then a and b gives the same remainder and the reverse integration also holds. Agree? Now come to the next arguments. Suppose a congruence to b mod m. If a congruence to b mod m and a congruence to b mod n. A congruence to, if a congruence to b mod m and a congruence to b mod n, a congruence to b mod m and a congruence to b mod n with m and n are relatively primes. With m and n are relatively primes, then a congruence to b mod mn. A congruence to b mod m and a congruence to b mod n with m and n are relatively primes. Then prove a congruence to b mod m. Let's again immediate from this definition. Why? For how to prove this one? A congruence to b mod m means a congruence to b mod m. That means m divides a minus b. M divides a minus b. Again, a congruence to b mod n. A congruence to b mod n, that means n divides a minus b. It is n divides a minus b. Okay. M divides a minus b and n divides a minus b. M divides a minus b means, what is a minus b? A minus b equals some m into q1. Okay. A minus b equals some m into q1. N divides a minus b. N divides a minus b means here a minus b equals some n into q2. Okay. A minus B is MQ1, A minus B is NQ2. Then it is clear, it is given and also given N and M are relatively primes. Now, N divides A minus B. Now again consider this, N divides A minus B. That means, what is N minus B? A minus B is MQ1. That means N divides from this argument, N divides MQ1. Clearly, that means N divides Q1. Why? Because N does not divide M. Since N and M are relatively prime, so clearly N divides Q1. N divides Q1 means Q1 equals sum N into C. Agreed? Sum N into C. Therefore, A minus B equals M into N into C. Why? Because from here A minus B equals MQ1. Substitute. A minus B is Mn into C. A minus B equals Mn into C means A minus B equals Mn into C means Mn must divide A minus B. Mn must divide A minus B. Mn divides A minus B means M minus B congruence to 0 mod Mn. A minus B congruence to 0 mod Mn means A congruence to B mod Mn. So if A congruence to B mod M and A congruence to B mod N, if with M and N are relatively prime, then A congruence to B mod Mn. Yes. So now let us discuss about the residue classes and complete residue system. Residue classes and complete residue system. So that we will discuss in our next class. Thank you.